Right. So today, in principle, for our first lecture, like more or less, I'll be trying to just reference like the sections in the book that we were going to be discussing. So roughly, this corresponds to 12.1, 12.2 on the book. Now, usually, I prefer also to give like the first day like more of a quick overview of what we were supposed to do in this course, so that you at least have an idea of where we're headed. And so let me just start doing that, and we'll do a little bit about these two sections near the end of class. Uh, so in many ways, like what we are supposed to do here is just take things that you already learned, but just look at them from a different perspective. So for example, let's start with something very simple, which is like the graph of a function, right? So to be even more concrete, let's say you're looking at the function y equals f of x, which is x squared, right? And you know the graph of this function is a parabola, right? So this is more or less what it looks like. So the graph in this case is a parabola. The name is not too important here. What really I want to emphasize of this graph is that the graph itself is like a curve on the xy plane, right? So this is some curve. Is that okay so far so good? So like, you know, so graphs of functions like on the xy plane, they look like curves. And if you think about them in this perspective, which is like the Calc 1 mentality, like sort of like you had the xy plane, which is like a piece of paper, you draw the curve, and so it's like almost like having like a static object, right? It's just like a picture, it's like a photograph, nothing is not, it's just the curve is given to you, right? Like you see the graph all at once in a sense. Okay, so here like you think of the graph in like some sort of static view of the graph, because the graph is sort of out there, has been drawn for you, and then you're just appreciating it, contemplating it in all its majesty. Now, here is like a more dynamic view of the same graph, right? Uh, Imagine that you have a particle, like a point, like a ball, a really small ball, so it looks just like a dot, okay? And let me do it here. So maybe you have a watch, and at time 0, right? The particle was here. Maybe at time 1, the particle is moving. So this, like, imagine that the dot has, well, I'll say something about that later, but like now the particle is somewhere else. It has moved a little bit, and you're taking at it at each moment of time like a picture, right? So the picture that you took here is at time 0. Here's your picture at time 1. There may be a time 2 is here, right? But like, you know, like there, like you start taking way too many pictures. So a more convenient way to deal with all this information is like you just like impose, like put one picture on top of the other, right? So if you start doing that, like you just start drawing a bunch of dots here, right? Like those are like the 3 dots that we had before. Maybe this one was a little bit closer to the origin, so let me put it here, right? So this was for 0, 1, or 2. And then but then like you say well, but obviously there were other instances of time in between. So you start imagining like maybe the dots were moving like this. Right? Because you're starting to take a bunch of pictures. You're a bit of a stalker with this point. And then, and if you were to somehow do this continuously, if you just take the pictures continuously, right, like almost like a video, like a movie, like you just get the curve back, right? Meaning that like one way to think of this parabola that I drew before is that you had this point, and as the point is moving in the on the plane, imagine that you put like some paint to the point, so it's like starts dripping like paint on the plane, so it starts tracing out a trajectory on the plane, and so the trajectory that it traces out is the parabola. Okay, and so from this point of view, like the parabola is just like the trajectory of a particle over time. Is that making sense so far so good? So I'm just saying, like, you can think instead of like thinking that the picture was sort of got given to you, like you see it all at once. Here, you're never like, you know, if you only see one of the frames, when you see one of the frames, you never see a parabola, right? Like here, we just see a bunch of dots. It is only when we combine all the frames together that we see the parabola itself. So like the parabola no longer sort of exists out there, completed. It's just that it comes into existence only after you put together all the different screenshots. Okay, and so what's like the advantage that this gives you? What does this buy you? Well, first of all, that means that you should think of this like curve maybe in a slightly different way. So maybe this was like the position x naught y naught, meaning that like this is a position at time 0, this is a position x1 y1. So those, like by that I just mean those are the coordinates at time 1, and these are like the coordinates at time 2. Okay, and so one, like the first thing that we want to do in this class is talk about vectors. And like what you should think about vectors is just as a way to keep track of this particle. Okay, so to keep track of something, like we need like a reference point typically. So not, like it's convenient to use the origin of the coordinate system as a reference point. So here's particle has a cell phone, so all their moves are being completely tracked because in the terms of services, it agreed to GPS locations. So you're the NSA, you're keeping track of the particle. And one way to do this from your command center is just like by drawing an arrow from the NSA to the particle. Okay, and this arrow that I just drew is called the position vector of the particle. So here, this is the position vector. Here's a different position vector, so let me use a different color. And here is a different position vector, so I will use a different color. Oh, this is a great question. Someone asks on the chat, t equals 0. Well, I suppose if the point overlaps with the NSA point, you sort of reach their headquarters, but then you just escape. Like managed to escape. So, uh, oh, it means National Security Agency. uh, the vector would be zero, correct? If you reach the origin, yes. Um, there was a private question on the chat of why, if whether t equals zero should be here. That's a great question. When I mean t equals zero, that just means like, when you have a watch, you have to like arbitrarily say where you start to begin like the timer, right? So t equals zero just means that the timer started at this point, that you just press the button for the timer to begin at t equals zero. So from that perspective, you're free to think that you started the timer somewhere. And so I'm just saying that I just made a convention that I wanted to start my timer where the particle was here. And so that's why I'm saying that this happened at t equals zero. I don't know if that makes sense. Is that making sense? Right. But this is a good point. If you sort of had reached on a fourth, uh, maybe at time 1.5, the particle coincides with the tower. So, and here, like the position vector is like you say it, like it's an arrow with no size. So, like here, like the position vector has no size. Is that making sense? So far, so good. Uh, I mean, like it's also like right on the right hand side. Like it's not that necessarily t equals zero has to be on the left hand side. Like on the negative, on this quadrant. Like you could also have like you could have like started. You could also have said that this was like t equals zero, but then this becomes like if you had said like this is t equals zero, then you say that this is t equals -2. If that makes sense. Oh, I just mean that the uh, um what we're when we're going to start talking about arrows or vectors. So a fancy name for an arrow in this class is just going to be a vector, basically. And so as you see here, you have one arrow, but you can imagine start shrinking it. So you have a smaller arrow, and then you can imagine that you start shrinking it again, and then you have an even smaller arrow, and then you just imagine that you can maybe shrink it to like the size of a point. So I just mean that there's a arrow that has no size. It has length 0, which means like you just collapsed it, right, like to a point. Yeah, no problem. Is that making sense? So like the point here is that so in general, like your dot will be somewhere on the xy plane, and so there will be like this position vector, which in general is called r. And this notation you don't need to worry too much about for now. I'm just saying that this is like the usual name that people give to these arrows. So this is called the position vector at position of particle at time t. Usually you draw like an arrow on top of the letter R to remind you that this name is associated to a specific arrow. Okay. And then the point is that like this is giving you like the x and y coordinates, like what will end up happening next week is that you'll think of this as giving you the x and y coordinates of the particle or this dot. But so like the x and y coordinates change over time, and so that's why you think of this as two functions of time. So what I'm trying to say is that really the way in which we're going to be thinking concretely about this position vector is that it gives you the two coordinates of the particle as functions of time. Is that okay? So I'm just saying like that now we think that both x and y depend on time. So like this is like the way to write that, to make that to emphasize that. And so like what, like the idea is that before when you had something like y equals x squared, like the way in which you thought about this was that y was a function of x, right? Here y is a function of x, right? Um, but now from this dot perspective, right? Again, like this dot tracing out the parabola, now both x and y are functions of t. So that's the difference between the 2 points of view. Is that okay? Is that making sense so far so good? Because now you're imagining that the curve is being traced out in space as you move. So that's why things are now changing in time. Yeah, this is, yes, like the way in which we will call this eventually is a parametric equation, if you want to use that terminology. Yeah. Is that making sense? So again, like we're sort of, at this point, we're sort of looking at the same object, but just from the two different points of view. So like just to give you an example, like about of the power of this different interpretation, let's go to forbidden land. So let's go to Wolfram Alpha. It's forbidden for the exams, but it's friendly for things that are non-exam related. So name a person that you find is a famous person who is interesting. Anyone? Maybe Newton. Okay, let's say who other, maybe, okay, good, good. Let's see what happens. Is there a Newton curve? There is. So here's your Isaac. I'm glad someone mentioned him. He's my favorite physicist. So you started well this semester. So here's the equation of your Isaac. Here's a curve. Here's the equation. This is the equation in terms of t for the x coordinate. The hair took a lot of time. And here's the equation for the y coordinate as a function of time. So you have to imagine the Isaac Newton curve. Yeah. The Isaac Newton curve was drawn by a particle moving in time, and this is how the particle was moving. Oh, sorry for that. And no, there is none. But there's none for LeBron, so like I don't feel bad. Now, so it's a quite complete catalog. uh, you can after we finish lecture. But this is just to show you the power of this perspective. How could you write this as y as a function of x? imagine doing that. Even if you were going to try to write this implicitly, like x squared plus y squared equals something, it would just be a mess. But with this parametric version, there's a chance of succeeding. Yeah, for the before graph, you don't think of x and y as yeah, they don't depend on anything else. Like it's just y, the one that depends on x, but x is sort of like the independent variable. Like if you prefer, you can use the terminology dependent and independent variable. So, well, I will let you try it to see if there is one. But this is let's go back to iPad. So what I was trying to say is that here in this perspective, like y is a dependent variable and x the independent one. In this perspective, both x and y are the dependent variables and t is an independent one. So maybe I should write that. It's just a different point of view. So like what I'm trying to say is that here y is dependent variable and here x is the independent variable, but here x and y are dependent variables and t is an independent variable. Does that make sense? The term, like the actual technical word that's used is that you say that t is like a parameter. So this is why this is called the parametric equation. But like for now, if you prefer to call it independent variable, that's fine. Uh, and so, and then for example, like say when you had, so like as we just saw, like curves can do crazy things. So you could do like, you could have like a curve doing like something like this. Again, this is being specified by x and y as functions of t. And so, you know, like in calculus, you talked about like tangent lines, right? In calc 1. So you could imagine like finding a tangent line to the curve here. But like the point of view that we will take is that instead of like thinking about tangent lines, we imagine like drawing a vector, right? I mean, really, this vector should be drawn like on top of the line. I just don't know how easy it will be to distinguish the two of them. But you draw like a vector which uh, starts at this point on the curve and points in the direction of the tangent line. And we'll see that this vector can actually be considered, this arrow can be interpreted as a velocity vector. So instead of like, so you can imagine that like to a curve, you can start drawing like these vectors that are tangent to the curve, these arrows basically, that start giving you like the velocity that the particle had at that moment in time. If you want, I imagine some of you have been to like Busch Gardens or all the parks in Florida. Like another point of view you could take is like this is like a roller coaster. If you want, you can still imagine that the curve is sort of given to you, but then you're like on the roller coaster. So the particle is moving on the roller coaster. So that's what you're keeping track of. And then you just see the velocity vector as a tangent vector, as an arrow drawn, which is tangent to the roller coaster or tangent to the curve, if that makes sense. Okay. And then you can take this a step further. Eventually, so like our objective for like the first weeks of class is just say, oh, so here you have a particle, you have its position vector. How do you find the velocity vector? How do you find the acceleration vector? So that's what we were going to start doing at the beginning of the course. And then like near the end of the course, like jumping ahead a little bit, uh, anyone remembers the name of the river of New Brunswick? Yeah, good. Then you have the Raritan River. Imagine you're just looking at the surface of the river, and so you want to understand like sort of like the water currents of the river at the surface level. So one way to do that is like you play with paper boats. So you have a boat, a tiny boat here, right? Because if it's too big, it will disrupt the water currents, and you just want to see how they behave. And so the boat is moving in space. Sorry, it's moving as time goes by. The boat is moving uh, along the river, and again, those are different screenshots, and I'm just putting them together. But like you can imagine that maybe the boat, like what like the boat was doing, was something like this, right? And so for this particular trajectory that this boat took on the river, again, you can imagine like drawing a bunch of arrows which tell you the velocity that the boat was having at this point on the river. Okay, but maybe some other person plays with another boat, but this one is an unlucky boat. So I don't know if you see what's sort of going on with these boats, but as you were moving, you sort of got trapped into a whirlpool. So the boats, this unlucky one is just getting going to be dragged in this whirlpool. So well, this is easier when you if you play with boats if you flush the toilet. So you can do science experiments with toilets. Yes, it's more likely that men get into trouble. So here's a whirlpool. And so you see what is happening is like at each point on the river, you could imagine like drawing just a bunch of arrows that tells you like what the velocity would have been of these paper boats. Okay. Oh, okay. So, yeah, I don't know the stats for the teams, but men do tend to be a little bit more erratic in general. Uh, and so you end up with what's called a vector field. And the idea of a vector field is just like an arrow that you drew at each point in space. So when someone tells you that there's a vector field, that's just what they mean. And like what we will end up doing at the end of the course is just basically try to analyze situations like this. So what sort of mathematical device will tell the both teams don't go to this region because this region has a whirlpool. So there's a mathematical way to measure whether or not there's a whirlpool. There's also like a mathematical way. If you think like maybe a bathtub is a better example for this and not a river, but you could have, you could have like a situation like this, like if you open a faucet, right? If you open a faucet, imagine like what you'll see is like something along these lines, because like liquid is pouring out away from the faucet, right? And so like you would say that this point P is a source, of water or fluid. But if you like again like the bathtub, imagine like just like the sink. So if you have something like this, and so like you could also try like we'll also learn ways to detect whether or not there are sources or sinks in say a given fluid or vector field. But the idea is like, and this will finish the overview. Like the idea is like really you can extend this idea of like vector fields to other things. So maybe you have heard about electric fields, for example. If you have an electric field, like say a proton, which is like a positively charged particle, as you may know. So like one way to conceptualize of a proton is that a proton is producing a bunch of arrows, which are called the electric field, and then oh, there's no even a men's thing. I see. And then like you would say that like a proton is like a source of electric field, but then you could have something, as you may know, as an electron, and so if you have seen this, probably some of you have seen this, that oh good, perfect. You will say that an electron is a sink of electric field. Okay, and there are more fun other things that can happen, but I may mention them as we go along. So this is like closer to the end of the course, but I'm just saying that like you like what this should tell you is like secretly you have been surrounded all this time by arrows, and I'm just giving you examples where you would come across them. Okay, and so what we have to do for the next couple of lectures is just talk about vectors. What are some of their properties? So maybe let me start, but in the remaining minutes just by telling you a little bit about them in more detail. So, and this is again roughly what corresponds to the material on sections 12.1, 12.2 of the book, more or less. Uh, if you want to be keeping track of that. So, about the vectors, like what you should think of them is like for now, I mean, there's a more profound way to understand them, but for us, like a vector will be something like this that I just drew. So a vector will literally be like an arrow of sorts. And so like the name that you give to a vector, usually you use the letters like V, U, or W for vectors. So here's like a vector. You put like an arrow on top of the letter just to emphasize the fact that it's supposed to represent some arrow. And for us, like the two main features of a vector is that it consists of two pieces of data. Um, One is the size, right? So arrows have length of or size. Oh, so like the first piece of data about a vector is its size or length, also known as the fancier names for this are magnitude or norm. So if someone tells you length, size, magnitude, norm, think of them as synonyms of meaning the official, like the same thing. Okay? And so say if this arrow were like 3 feet long, like you would say that size of this vector is 3 feet. So you would write something like this. So by this, I just mean this expression represents the size of a vector. This expression also represents the size of the vector. So this is telling you the size, which is also the same as the length, which is also the same as the norm, which is also the same as the magnitude, which in this case happened to be 3 feet. Okay, so all of these like are sort of interchangeable names or like expressions for the same thing. Okay, is that making sense? So it's like, I mean, it's sort of, it's just so used, I guess, that's why you ended up having so many different names for the same thing. And so like the first thing of like what makes a vector is that it has some size. And the second thing of a vector is that it has a direction. So, and this is like the thing that's maybe a little bit new of compared to other things that you have worked with. Yeah, great point. I'll talk about the zero vector. The zero, there will be a special vector called the zero vector, which is the only one where the size is allowed to be zero. Uh, so size zero counts as size, but it's just, I mean, is it's just convenient to call that a vector as well. So it's stretching a little bit the concept because it has no size, but it's just useful. You'll see why um, next time. But yeah, there will be, and as an exceptional case, like there will be a vector with no size called the zero vector. Uh, it's almost just that. It's slightly different. Like the thing that will, like again, like I don't want to say this right now, but like for example, this is the number zero, right? The vector zero will be something like this. I don't know if you see the difference. It's almost the same, but quite a little bit different just because like vectors are supposed to have entries, and I'll explain that next time. So like there's a difference between the number zero and the zero vector just because the zero vector has entries, but the entries are zero. So almost no confusion would arise if you forgot about the difference. Like because almost with anything with zero, almost it's very straightforward what happens if you work with something with zero. So uh, now the yeah, so vector space. Uh, well, saying what a vector space is, it's a deep question. It's just that I mean, uh, it's like that's something that's discussed in linear algebra, but the short answer is that you can think of a vector space is a space that is inhabited by vectors. So, like in a sense, like you can think that there's a universe, like like the elements of the universe are vectors. Like it's just a little like it would take a little bit more time to explain accurately what a vector space is, but it's just if you want to be more pragmatic, it's just like a fancy name for a collection of vectors, but it does have many specific properties that makes you think of it as some sort of space. But yeah, it's just like think of vectors as creatures. You can make a zoo of vectors, and the zoo of vectors is a vector space. Like it's where the vectors end up living. But yeah, you would need to take linear algebra if you want like a precise definition. Yeah. Like this, the beginning of this class overlaps a little bit with linear algebra. My understanding is that apparently in statistics, you also talk a little bit about vectors. I'm not sure. Yes, it's related to the span of a matrix, but again, it's a little bit. The span of a matrix is an example of a vector space, and it's a little bit more complicated. But yeah, it's you're getting hot, like warm, cold, cold, warm type game. You're getting close to the truth. Yeah. So, so what do I mean by vectors having a specific direction? So again, here's a vector, right? You have this arrow. It has a size, but it's pointing like towards my ceiling. Now I change its direction, right? Notice that I just rotated the vector. So actually I didn't change its size. But still, because I changed its direction, we're considering these two vectors to be different, if that's okay, if that makes sense. So the moment you change where the vector is pointing, it doesn't matter uh, if the size did not change. Just because the fact that the direction changed, they're regarded as different vectors. So what I'm trying to say is that these two are different vectors, even if their sizes are the same. Is that okay? Is that making sense? So by the same token, if you had not changed its size nor its direction, then you think of the vectors as being the same. So if I had taken something like this, if you just start cloning the vector, you really think of them as copies of each other. So they're really representing the same vector. Uh, exactly. That's like where we're headed. But I'll say this next time. The fact, like, so the idea is that sort of like vectors here, like they're like on in the wild. They haven't been captured, so vectors can be put anywhere in space. Once you have a XY coordinate system, right? You want to drag the vector so that they begin at the core at the origin. So since you're free to move vectors around as long as you don't change its size or direction, once you specify a XY axis, you sort of drag it so that it starts at the origin, if that's okay. So, but in a sense, like right now, there's no reference point, but for practical purposes, we will always have a reference point. And when we have a reference point, they will always start from there, basically. I don't, is that okay? Yeah. So like for now, but for now, yeah, they're just sort of out there. Uh, Now, other things like that you could do with vectors, say if the vectors are pointing in the same direction but have different sizes, then all of these vectors are called parallel. So, okay. And so, and maybe finally to finish in the last 3 minutes, like the another thing that you can do with the vector is sort of rescale it, meaning that you could have like a vector v, and what would be 2v. Well, if I write something like 2 times v, I mean like the same direction. It's a new vector that has the same direction, but it's twice as big. So it's twice as big, but same direction. On the other hand, if I were to write like say negative 1/2 v, or let me just say, if I were to write negative v, what I mean by that is that it's same size, but you have to reverse the direction. And then you could like also do other combinations. Like for example, you could do like 1/2 or 1/3. Is that making sense? So like what I'm trying to say is like if you take a vector, like you can imagine like again, like stretching or contracting that arrow. And so when you do this rescaling, you just specify that by the number in front of it. So this number in front of it just tells you the rescaling factor relative to the original vector. So this is twice as big, this is same size but opposite direction, and this is a third of the size but same direction. So if there's a negative sign, that means that you had to flip the like the it has to point in the exact opposite direction. Is that okay? Uh, and so, well, we don't have much time left. So, like, the idea is that what we were going to do on Monday is that, so, like, in the same way in which you can add numbers, like, say, 1 plus 3 equals 4, there's a way to add arrows. So, we're going to talk about how to add arrows. That's not too difficult to do. What's a little bit more interesting is how to multiply arrows. That's a cool thing to try. So, because you can multiply numbers like 2 times 3 equals 6. So you could ask, well, is there a way to multiply arrows? There are sort of two ways to do it. One is called the dot product, and the other is called the cross product. And we'll talk about the difference. I mean, we'll start with the dot product on Monday. We probably will not have time to talk about cross product, but you'll see I guess the emphasis, what I want to emphasize is now once you start talking about arrows or vectors, there's more than one way to reasonably multiply them. So it's just that both ways end up being useful. So that's why you keep track of the two operations. And so yeah, I'll see you on Monday. Again, there's recitation tomorrow, but it's optional. Well, I mean, sort of optional, but it's still the same. Yeah, I can stay a bit longer if someone has questions. I'll probably just finish the recording right now. But yes, if someone needs to stay to ask me questions, that's fine. So yes, I'll stop sharing. I'll stop recording, and if that's okay, I'll see you on Monday. Well, but preliminaries on Canvas, I think it's just like review material from Calc 1 to Calc 2.